Welcome to lecture 9. So, in this lecture, we study mean value theorem. So, detail of the contents of this lecture is following. So, topics. So, first we recall mean value theorem for real valued single variable functions. Okay. So, mean value theorem for real valued single variable functions. Single variable functions. Then we give an example. Then example. So to show that mean value theorem for real valued single variable function is not true for vector valued several variable functions. Then we generalize the theorem, mean value theorem for real valued single variable functions to vector valued several variable functions. Okay, mean value theorem for vector valued several variable functions. So this is functions. Then finally, this is last part. This is applications. So we have two parts. This is part 1. So there are two parts of the video. This is part 1, this is part 2. So okay, so let us start with mean value theorem for real valued single variable functions. So recall the statement of the theorem. So this is theorem 1. Let, so this is the statement, let f is a function from R to R be continuous on close interval a comma b and differentiable on open interval a comma b. Okay, then the conclusion is, then there exists a point C in between a and b. So C belongs to open interval a comma b such that f of b minus f of a equal to f prime of c. So the derivative of f at c times b minus a. So this is the statement. So we label this equation by equation number 1. Okay, so so we note that the quantity f of b minus f of a over b minus a. So what is this? This is the slope of the line through the points through the points a comma f of a and b comma f of b. So this is line in R2. Okay, so so this is page number 1. So let us go to the next page. So this is page number 2. So if you have 2 points a comma f of a and b comma f of b, okay, then there exists a unique straight line, Euclidean straight line through them, okay, and the slope is given by f of b minus f of a over b minus a. So this is the slope. So what is slope? This is the tan theta, which is equal to tan theta. What is theta? Theta is the angle. So angle of the line with x-axis. So this is theta. Okay, and so on the other hand, so of course here b is not equal to a. On the other hand, what is a prime of c? A prime of c is, and f prime of c, or in general a prime of x, this is the slope of the tangent to the graph of f, to the graph of f at the point x comma f of x. Okay, so suppose this is R2 and this is the graph. Okay, suppose this is point x. So here we have x comma f of x, and what is tangent? This is tangent. Okay, so this is tangent. So if this is theta, then tan theta is the slope, which is equal to f prime of x. Okay, therefore mean value theorem says that given any chord, so let us draw another picture. So suppose this is so suppose this is a and this is b. So here we have a comma f of a, okay, and here we have b comma f of b. So this is let us denote it by denote this point by a, and this is the point b. So given any chord, so what is chord? The line segment, straight line segment joining these 2 points, this is a chord. Okay, so given any chord of a smooth curve, of a smooth or differentiable curve, we can find what? We can find a point. So point C, okay, comma f of c. So some point on the graph of the function, okay, So we can find a point lying between the endpoints, lying between the endpoints, between these 2 points, between the endpoints of the chord, such that the tangent at that point so here the tangent, this is the tangent this tangent has equal slope as the chord. Okay, that is the tangent at that point is parallel to the chord. So this is the geometric interpretation of mean value theorem, and so we will not prove this theorem, but so this is page number 3. So but give an idea of the proof of theorem 1. Okay, so to prove we use Rolle's theorem. So we use Rolle's theorem. So to use Rolle's theorem, we define a new function g, define g of x equal to f of x minus r times x, where r belongs to r is a constant, such that g of a equal to g of b. So and we have g of a equal to g of b, so that determines the value of r, and g of a equal to g of b. So we have if and only if r equal to f of b minus f of a over b minus a. So please check it. And so therefore for such a value of r we can use, so now g is continuous on closed interval a comma b and differentiable on open interval a comma b. Fine. Therefore Rolle's theorem implies there exists a point C in the open interval a comma b such that g prime of C equal to 0. Okay, and that implies, so what is g prime of C? G prime of C equal to f prime of C minus r, and which is equal to 0, and this implies f prime of C equal to r, and value of r equal to f of b minus f of a over b minus a, and this implies f of b minus f of a equal to f prime of C times b minus a. So which is equation number 1. Okay, so this is basically the proof of uh, mean value theorem for real valued functions with single variable. Now we remark here page number 4. So we remark that mean value theorem, that is theorem 1, or we may say equation 1 is false for vector valued functions. So in general, in general, okay. Yes. So to justify this statement, so it should give an example. So consider the following function f from R to R. So vector valued functions f from R into R m. So here we are taking n equal to 1 and m equal to 2. Consider the function f from R2 to R2. So R2 R2 defined by f of t equal to cos t comma sin t, and a equal to, let's say, 0 and b equal to 2 pi. Then f of b minus f of a, this is equal to f of 2 pi minus f of 0, and this is equal to f of 2 pi means cos 2 pi comma sin 2 pi, and that is equal to 1 comma 0, and f of 0, that is also 1 comma 0, and which is equal to 0 comma 0. And on the other hand, f prime of t, okay, this is equal to minus sin t comma cos t, and f prime of t then has norm equal to uh, 1, and b minus a, which is equal to 2 pi minus 0, so which is equal to 2 pi. So for any t belongs to R, okay, for any t belongs to R, f prime of t times 2 pi, okay, this is not equal to 0 because its norm is has norm 2 pi, okay, so its norm is 2 pi. So this is not equal to 0, therefore we have f of b minus f of a not equal to f prime of c acting on b minus a, okay. So this is counter example. But so next page is page number 5. So now let f is function from R to R2. So suppose this is a differentiable function, okay, and a equal to a1 comma a2, any point in R2. Now we define big F from R to R. So real valued single variable function defined by f of t, this is equal to a dot product with f of a. Okay, so basically this is equal to inner product a comma f of, so this is not f of a, this is f of t, f of t. Okay, so this is the function. Then f is differentiable. Now for any x comma y in f, so in R, so by theorem 1 we have, so what we have, f of y minus f of, so no, we are applying mean value theorem, theorem 1 on big F. So f of y minus f of x, so this is equal to f prime of c, okay, times y minus x. Where c lies in between x and y. So what is this equation? So this implies, so what is f of y? F of y means a dot product with small f of y minus a dot product with small f of x, and this is equal to, so here the derivative of big F at C, this is equal to a dot small f prime of C. Acting on y minus x. So here it is dot product, and this is real number and this is real number. So here this is product of scalars. Okay, and this implies a times f of y minus f of x. So a dot product with f of y minus f of x, so this is equal to a dot product with f prime of c times y minus x. So what, so this is statement similar like mean value theorem. So here we can see that for um, for a, for any point a equal to a1 comma a2 in R2, okay, so there exists a point C lies between x comma y such that a dot product with f of y minus f of x equal to a dot product with a prime of c, okay, so times y minus x. So this is true, and in particular, so next page is page number 6. So in particular, if we apply this uh, in example 1, so in particular in the example, so in the example f of t equal to cos t comma sin t. Okay, so this is the function we have considered. Then f prime of t, this is equal to minus sine t comma cos t. Okay, and so we have considered y equal to, so b equal to 2 pi and a equal to 0. So f of b minus f of, okay, so well, so let us use a different symbol. So x equal to 0, y equal to 2 pi. Okay, so here it is 0, here it is 2 pi. So we must have some point c over here such that f of 2 pi minus f of 0 equal to a1 comma a2 dot product with a prime of c, that is minus sine c comma cos c, okay, times y minus x, that is 2 pi, and this left hand side is 0. So and what is the value of this dot product? This is equal to a1 sine c, we have a minus sign, and plus a2 times cos c. So this is equal to 0 because 2 pi is not equal to 0. So this implies um, mm, tan c. So tan c equal to a2 over a1. So provided a1 is not equal to 0, if a1 is equal to 0, then tan c, that is that tends to infinity. So this implies c equal to tan inverse of a2 by a1. Okay, so one can see that the interior point c depends on a equal to a1 comma a2 in R2. So go to the page number 5. This is the previous page. So here so existence of this point c depends on a. Okay, so therefore uh, for given a, there exists a c lies between x and y, and this c should depend on a. Okay, so let us stop this video here, and in the next part, that is in part 2, we generalize mean value theorem to vector valued several variable functions. So